All right, we are recording. We are live. You should be able to hear me and see me as well as the screen. So, everybody, welcome back to Senior Seminar. Welcome to our FE review. We're going to continue on with our FE review schedule. I'll go ahead and tell you. Homework 3 was your first FE exam quiz. I looked, and most people had completed that before the morning started, so that was good. I'm going to have another quiz available later today. It's usually it would turn on at 1 p.m. Honestly, it probably will be like 2 or 3 before that gets finished. I wasn't able to get that completed and whatnot. I had to cover some other sections this week, so had a pretty busy week this go around. What I'm going to do is get that uploaded later today, and then homework 2, the homework that you all had on the FE exam or the licensure process. I'm going to hopefully get that graded by the end of the week, and then we'll keep on trucking. Again, with the quizzes, I'm not grading based on how well you do. I'm just grading that you completed it. So don't let the grade for the class get in your way. Just give the quizzes your honest effort. I'll go ahead and tell you they are intended to be, I don't want to say difficult, but they're intended to be challenging. So the idea is to put you through the ringer and let you know like what you did well, what you didn't. And I'll get the solution for that quiz posted later on today. That last quiz, not the one you're about to take, later on. Okay, any questions before we jump right into it? Well, I have my FE approved calculator. Hopefully you have yours. Let's jump right into it. So we're continuing with mechanics of deformable bodies, or mechanics of materials as it's referred to on the exam. What we're going to do is, so I put together the review and I started looking at the topics that are covered in mechanics of materials. I'm not going to cover shear and moment diagrams because we can cover that in a structural engineering topic if we want to do that later. In terms of stresses and strains, so we've done axial, we've done torsion, we've done bending. Today we're going to do shear and thermal. We've done, and if you could do the stresses and strains, the deformations that go along with that, it's all kind of together. And then there's the other topic, which is Mohr Circle. So we're going to cover that today as well. So let's jump right into it. Let's start off by talking about shear stress. So what's going on with shear stress? Let me see. Actually, this would be a perfect example to use a prop. So I think just about everybody in here is comfortable, or hopefully you're comfortable with sigma equals my over I. It's very, very commonly used in engineering applications. We use it in concrete design and steel design and all that stuff. And so what that's talking about is taking a section and bending it. Okay. Now, when you bend a beam, usually what's going on is you've got the beam is supported, maybe something like this, and you're bending it. Maybe you've got a load that's placed on top of it. And so by now, just from what we've done in structural analysis and all the classes that you had with me up until now, that when you do that, not only do you generate a bending moment, but you generate a shear. Okay. Now, I think that hopefully the shear diagram and determining the shears is pretty straightforward, because I mean, if you could draw a moment diagram, you could draw a shear diagram, and that's where you get your shear forces. But the resulting shear stresses, I've found that sometimes students are a little bit confused about that. So first off, I want to make sure that everybody's clear, like the physical aspect of where they come from. Now, here's a book, okay? Now, what is a book from a mechanics perspective? Well, one way of thinking about a book is it's just, what is this, like hundreds of really, really, really thin beams, okay? Now, if I take this thing and I bend it, what happens is the pages, they freely slide from one another, freely slide. And so I would argue that this book, for the sake of the discussion, has no shear resistance, because the pages, they slide against one another. There's shear developing, in the beam, but the pages aren't resisting it because they're just going. So imagine if I took this book and I super glued all the pages together. I had, oodles and oodles of time, and I super glued the pages together. What would happen is I would essentially turn this book of a bunch of paper into basically a block of wood, because when I start bending it, the pages can't slide against one another, and now what we've got is a beam. We've got a beam that resists those shear forces. See, from a mechanics perspective, what's happening is, let me pull my slide up here. So what's happening is when you have a beam that's being bent, I think everybody's kind of familiar with this. This is the sigma equals my over I. Well, this is on one side of the section. I mean, you all know that bending moment diagrams, they change, right? If I cut a section here versus cutting a section, 2 or 3 feet down the beam, I'm going to get a different bending moment on one side of the beam than I am the other. So there's a different bending moment on the left than, say, there is on the right. And so from an equilibrium perspective, if I'm looking at, let's say, forces in the x direction, I can't have a different bending moment on one side of the beam I do another, because if I just look at them in an equilibrium perspective, it's not going to match. There's a differential between the forces on the left side and the forces on the right side. So how does that square? How do we still get sum of forces in the x direction equals 0? Well, in the beam, you develop a shear stress. In between those layers of the beam, you develop a shear stress, and that's where the equilibrium comes from. Okay. Now the formula to compute that shear stress is tau equals VQ over IB. The V is simple. That's just the shear wherever you're cutting a section. That's pretty straightforward. I is just the moment of inertia. But let's talk about B and let's talk about Q. Okay. So B is the width of the beam. Okay. And I'm not going to get into the derivation of where this formula comes from. Just take my word for it that that's the equation. But B is the width of the beam. Okay. Now, if you look at the stress profile of various beams, and this is this image here on the bottom right, what you find is that the bending stress profile doesn't really change, but this is the shear stress profile. So, this would kind of be what the shear stress profile looks like for a rectangular section. And this would be what the shear stress profile looks like for an I-beam. And so with both cases, you get your maximum shear stress in the middle. But what you find is that for the I-beam, you get this sudden jump, so here's some stress, and then boom, the stress gets a lot bigger. And the reason why there's a shear stress jump is because at that point, the beam suddenly gets thinner. You go from this really, really wide flange, here you've got this really, really wide section, to suddenly the width gets really, really tiny. So there's a jump in the shear stress profile. It's like when you're looking at steel design, you basically just say, okay, the flanges carry the moment, and then the web carries the shear. Just because of the way that the distribution of shear stress goes, all of the shear stress tends to be in the web, and so that's why you do that. Now Q is the first moment of area, so it's basically just an area times a centroidal distance. The example that we're going to do today, if you're a little fuzzy on that, it's really simple. So that'll be clear here in a second. Speaking of, let's just go ahead and jump right into an example. So I have a rectangular beam that's 4 centimeters wide and 6 centimeters high, and it's subjected to a shear force of 7,000 newtons at a particular location. So I drew the shear diagram, cut a section, and I'm looking at this particular point, and the shear is 7,000 newtons. The beam is constructed of some type of aluminum. You'll spoiler alert, that actually doesn't matter. It's very rare that happens on the exam, but and this is really sort of for me teaching you, that's a superfluous. It doesn't really matter in the problem. So think about it like this: if I have a bar, let's say I have axial stress, sigma equals P over A. If I got 100 pounds on that bar and it's 2 square inches, then the stress is 50 psi. It really doesn't matter if the bar is made out of wood or steel or concrete. Just sigma equals P over A. And so the same thing here. We've got a force. We're trying to determine the stress. What the beam is made of doesn't really matter all that much. And so what is most nearly the maximum shear stress at that location? And so we're going to do a shear stress calculation. And it's not hard. I think you'll find this is pretty straightforward. So let me break out the notebook and we'll jump into it. So all right. And if anybody has any questions, let me know. but we'll jump right into this. Okay, let me take my keyboard off. Okay, so we have a rectangular beam that's 4 centimeters wide and 6 centimeters high. When this problem was generated, we're really not worried so much about units. This is more about methods, so that's why everything's consistent with the units. We have newtons and centimeters, and it's just newtons per square centimeter. So we don't really have to worry so much about the units on this problem. Now, here's the formula we're going to use. Tau equals VQ over IB. Tau equals VQ over IB. So it's a question from structures. I'll have to look at that here in a bit. Okay, so let's see what we know. Okay, we know that, we know that V is 7,000 newtons. Okay, now we know the dimensions for the beam. We know that B is 4 centimeters, and we know H is 6 centimeters. See, so we already know B and we know V. Now, if we know B and we know H, we can compute the moment of inertia. So, pop quiz, what is the moment of inertia of a rectangle? Hopefully you remember that.
BH cubed over 12.
There we go, BH cubed over 12. So this is 4 centimeters times 6 centimeters over 12, which is, let's see, I have that done right here, 72 centimeters to the fourth. Okay, so think about the expression. We have VQ over IB, we got V done, we got I done, and we got B done. And so the only thing that's maybe a little bit fuzzy is this Q term, okay? And if you understand this, this is really, really simple, okay? So let's talk about Q, all right? So here's the beam. This is B and this is H. Now, first off, you know, I am sort of maybe cheating a little bit by understanding right off the bat that whenever I have a beam, like 99 times out of 100, the maximum shear stress is going to be in the middle. Like this is about what the shear stress profile looks like. It's like when I have like the bending stress. Like the bending stress looks like that, and then the shear stress looks like the image on the left. So, so this right here, this is going to be, you know, tau max, which is what I'm after. I mean, the problem is asking for maximum shear stress. Okay, so that means I need to determine Q at this region in the beam. I need to determine Q for basically this region. Okay. Now, Q is a first moment of area. What do I mean by moment? Moment is defined as, you know, a quantity times a moment arm, right? So like if we're talking about a moment of a force, it's a force times distance. If we're talking about a moment of an area, it's an area times a distance. So, you know, here we go. What is the area of this shaded region? Well, it's B times H over 2, or pretty straightforward. Okay. Now we need the moment arm. So maybe we'll call that term Y. Okay. And so what do I mean by moment arm? Well, what I mean by that is this. So this shaded region has a centroid that's maybe something about like that, you know, where that little plus sign is. How far is it from there to our centroid of the whole section? That's Y. And so Y, what is that? H over 4. So 6 centimeters over 4, or 1.5. So therefore, Q is AY, which is 12 centimeters squared times 1.5 centimeters, 18 cubic centimeters. And so there you go, VQ over IB. We got the V, got the Q, got the I, got the B. So it's pretty plug and chug at this point. Oh, I'm being sloppy. I can do better than that. And I'm a popular guy. I'm getting all sorts of messages on Teams. So can somebody give me an answer for this towel? I don't want to be the only guy talking or the only guy doing stuff.
All right, well, if I did my math right, according to the equation, I got 437.5 newtons over centimeter squared.
All right, anybody else get that? You know me, I always ask for seconds. Yeah, there we go. And so if I look at my problem, I ask myself, what is most nearly the maximum shear stress at that location? 440, which again, the FE exam, one of the most common phrases that you'll see is the term most nearly, okay? A lot of times, first off, I think it depends on the section. So for instance, if you have a problem in the math section, it's like, what's the derivative of x squared? It's not most nearly 2x, it's 2x. But any of these problems that involve computations, and particularly computations built upon themselves, you know, you have a formula, you get a value, then plug that into the next formula and plug that into the next formula. The reason why the choices are written this way is because they don't want rounding or stuff like that to trip you up, that, you know, the answer is 440, you know, and depending upon how you did it and how you rounded it out, there's enough buffer in there to for that to not be a problem. So that's generally how the exam works. All right. Listen. Like I have a bad taste in my mouth, but then I drink more coffee. All right, any questions? I know we did that pretty quickly, but I guess my overall point is that it's not hard. Again, this is the fundamentals of engineering exam. It's not trying to be, you know, space age stuff. Okay. Let's stop the share and let's go back to our notes. Okay, so we did a problem on transverse shear. So, you know, we've done axial loads, we've done torsion, we've done bending, we've done shear. There's one more stress that we kind of skipped that I want to talk about, and that's thermal. Okay, so, you know, if we look at looking at, you know, axial loads, what I have here on this slide is actually a much more formal way of expressing how we would determine thermal or axial stresses and axial strains and all the total axial response. And this comes directly from when I teach mechanics of materials. So when you have a member, like when I say an axial member, a member that's longer than it is, you know, wide and deep, maybe something like this I shape. I propose that the way that you would express its total axial response or axial deformation is a function of either its mechanical deformation or its thermal deformation. So what I mean by mechanical deformation is just PL over EA. So that's what I have there in the upper right expression. Just, you know, and that's a formula. I mean, we dealt with that last week, and that should be pretty straightforward. Now, what I have here on the left, to be honest, you could probably kind of ignore what I got going on here. You could ignore that. But the long and short of it is, like, if you really wanted it fancy, the formula on the right, PL over EA, assumes that the load is constant, and it assumes that the area is constant. In other words, you could have a member that it's really around at let's say the fixed end, but then it sort of gets narrower, like a tapered member. And if the member was tapered, you couldn't use PL or EA. You have to integrate. Or what the load changed. Instead of a pull load at the end, it's like a distributed load. So, like, actually, the way I'm holding this I-beam right now, this is not a constant load. This is a distributed load, because as the I-beam gets longer, it gets heavier. So I'd have to integrate that as well. Now, that's mechanical load. That's actually taking an element and loading it, pushing on it or pulling it. What about thermal effects? What if you take a member and heat it up, or take a member and cool it down? Well, the way that we compute that response is basically with this expression right here, okay? And so I propose that if you have a member like this and I heat it up, it's going to get longer. Or if I cool it down, it's going to get shorter. It's sort of like if I blew up a balloon and I took the balloon and I stuck it in the fridge. Give it some time, and when I look at it, that balloon's going to be tiny, because when it got cooler, it contracted. Same thing if I were to take that balloon and heat it up, it would get bigger. And so the way that we compute the axial elongation, so if I took this I-beam and I heat it up, it would get longer. How do I determine that axial elongation, that change in displacement? Well, I take the change in temperature, delta T, I multiply it by the length of the member, and then I multiply it by this term alpha. And alpha is a material constant. It's something that is unique to steel, or to brass, or to aluminum, or to concrete, or to plastic, or whatever. Alpha is what's called the coefficient of thermal expansion. So every material has its own unique alpha value. Just as a side note for you civil engineers in the room, which is everybody, one of the things that's kind of serendipitous is that the alpha value for steel and the alpha value for concrete are actually very similar. So when you have, like, bridge elements, for example, that are out in the field, take a bridge like in West Virginia. That bridge could get up into the 90s in the summer, and then in the winter you could be below zero. But those coefficients of thermal expansion for those two materials are very similar. They're not exactly the same, but they're pretty close, so that you don't have to worry too much about like the rebar shrinking at a different rate than the concrete, and that you get cracking from that. I mean, it can happen a little bit, but it's pretty nifty that they're pretty close. Okay, but back to the review. Okay. So this is a problem. I've actually never done this problem in FE review before, but the exam changed a bit, and they added thermal as a section for the civil. So I said, we kind of need to look at that. So I have a bar. This is a 12.5 millimeter diameter steel rod, and it's pinned between two rigid walls. Okay. So what I've got here is I've got just a bar like this. Let's say it's just pinned between the walls, and the rod is initially unstressed. So imagine I had a brick wall here and a brick wall here, and I just stuck the rod there. And then what I do is I take that rod and I heat it up. Okay, so you can imagine what's going to happen, right? If I've got this rod sandwiched between these two walls and I heat the rod up, that rod's going to want to expand. Okay, now buckling isn't an issue. We're not going to worry about buckling. So we can sort of ignore that for now. Now the rod's made of steel, so we know its elastic modulus is 210 gigapascals, and its coefficient of thermal expansion is 11.7 times 10 to the negative 6, and then it's 1 per degree Celsius. So alpha values, first off, alpha values are really tiny, so they're really, really small numbers. So just be aware of that. And then the units are always like per degree Celsius, because the idea is this is how much it expands. Like, this is the strain that you get per change in temperature. So if you multiply that times 50 degrees, you would get the thermal strain. Multiply it times the length, and you'd get the thermal displacement. And the question is, what's the approximate axial force in the rod? Which I think it would make sense that you get some axial force in the rod. You take that rod, you sandwich it between those two walls, and you heat it up. That rod's wanting to bow out, and so the wall's keeping it back. So the rod's actually experiencing compression. We're trying to figure out how much that is. Okay. All right, so let me stop share, go back to the notebook. Okay, so let me go down a bit. Man, is my screen froze or something? There we go. That's a little better. Oh, I need to move that down. That's my next example. Down it. Okay. So here's my problem. I've got a 12.5 millimeter diameter steel rod. This problem is going to be kind of a two-part problem. It's a little bit involved, so we're going to take it one step at a time. And I've found that the easiest way to do these types of problems is just to handle each part separately. To look at the thermal part and then look at the mechanical part. So our formula for thermal displacement is alpha L delta T. Okay. All right. Now, again, just, this is a thermal displacement. If I was looking for a thermal strain, it would just be alpha delta T. Because remember, strain is the change in length over the original length. So all I'm doing is just throwing the L in for the strain. So, super magical there. Okay, and so this is my formula for thermal displacement. And let's just use this formula, and then we'll talk about what it means and how it plays into the problem. So what do I know? I know that alpha is, 11.7 times 10 to the minus 6, and then that's 1 per degree Celsius. I know that the length of the member is 3.5 meters. I'll go ahead and tell you that it's probably a good idea to go ahead and convert this to millimeters now. The reason why is because if you look, this is in millimeters. If I calculate a displacement, I probably want it in millimeters. Kilonewtons over millimeters squared is gigapascals. So maybe I should have been more formal, and I should have said force is kilonewtons and length is millimeters, just to be formal. All right, my change in temperature is 50 degrees Celsius. So therefore, let's just compute this delta L, and we'll see what it means. So I'm just delta T. So delta T is alpha L delta T, which is, what is that, 11.7 times 10 to the minus 6, 1 per degree Celsius, 3,500 millimeters, and then 50 degrees Celsius. Just to make sure everybody is awake and got their coffee in them, what is the result here when I plug and chug? And we'll say, like, I don't know, 2 decimal places. Again, doesn't need to be super duper accurate. It's the FE exam. .05 millimeters. Do I have a second on that? Good deal. Okay, so let's just take a step back and understand what we just did. Okay, so here's a bar, and that bar was heated up 50 degrees. Now I propose if you have a bar and you heat it up 50 degrees, it's going to expand by 2.05 millimeters under these conditions. But here's the problem. The bar isn't expanding 2.05 millimeters. Remember what's going on. That bar is sandwiched between 2 walls. So what's happening is this. The bar wants to expand 2.05 millimeters, but the wall is pushing it back. 2.05 millimeters. Remember, here's what's going on. Delta total is delta mechanical plus delta thermal, okay? And when it's all said and done, the total deflection is 0, okay? So I propose what's happening is the temperature wants to expand that bar by 2.05 millimeters. The wall is pushing back with some force. I don't know how much force it is, but that force would cause a displacement of negative 2.05 millimeters or 2.05 millimeters in compression. So now what we have to do is we have to ask ourselves, okay, we have a bar, we know what material it's made out of, we know how big around it is, how much force would cause it to displace 2.05 millimeters? Well, how do we do that? Well, I know how we do that. We recognize, let me scroll down a bit. Oh, my example 3 keeps popping up. Let me move this down again. Cool. Is there 2 of those? I guess there's 2 of them. Maybe I accidentally, yeah, I must have had 2 of them. All right. Okay. Let's look at this. How do I compute mechanical displacement? Well, isn't it just that formula there? Well, let's talk about this formula. What do I know? Well, my mechanical displacement has got to be 2.05 millimeters. And you can, if you want to keep it negative, you can. It won't really matter. But if you want to be a purist, you can keep that negative. The P force, I have no idea. That's actually what I'm trying to figure out. What's the compressive force in the bar? That's the goal. The length, I know that. E, they told us that. What was it? It was 210 gigapascals. And then the area. Now, I don't know the area, but I do know that D is 12.5 millimeters. I mean, it's a round bar, and I know the diameter. Well, if I know the diameter, this is starting to get pretty straightforward. A is pi over 4 d squared, which is pi over 4 times 12.5 millimeters. Somebody help me out. What's that going to be? You might want to check your exponent. Did you square it? Yeah, I got what Khalid got, although it's square millimeters because it's an area. Yeah, there you go. 122.72, there you go, millimeters squared. And if the displacement is PL over EA, how do I solve for P? Well, multiply both sides by EA and divide by L. So 210 gigapascals, 122.72 square millimeters. Use that 2.05 millimeter displacement, put all that under 3,500 millimeters. And all my units already work out because everything's in millimeters and it's in kilonewtons because I got kilonewtons per millimeter squared is gigapascals. And so what do I get? Anybody have an answer for me?
Uh, 15.1.
15.1. And what are the units going to be? That's a force.
Okay. Let me see. Well, we have to convert it to kilonewtons, though. Wait, pascals is newtons over meters.
Well, here's the kicker. Here's the kicker. Keep in mind, this is a little shortcut. Whenever you have a kilonewton divided by a millimeter squared, that works out to be a gigapascal. So this is a force, so it's just going to be kilonewtons. Now, you got 15.1. I want to see if somebody else got 15.1. Good deal. All right. That's what I like to see. Okay. All right. Are there any questions about this? I want this to, make sense. I want this to be clear. All right. Let me clear this out. I was checking my math on the next problem. Cool. Okay. Now, let's talk about the topic that I think that many students I have learned find this to be inordinately complicated, but it's really not. And that's Mohr Circle. Now, the first point I want to get across about Mohr Circle is I am a firm believer that these problems on the FE exam are free throws. They really are, because they are straight up plug and chug. Okay. The thing about these problems is you just kind of have to be able to interpret what's given in the problem and plug and chug. But actually, I'm not even really sure that you have to do all that, because again, a lot of them are plug and chug. But let me be clear. I do want to make sure, I don't want you all to just be, grunt mechanical equation solvers. I do want you to have an understanding as to what you're doing. So let's talk about what Mohr Circle is and what it means. Okay. I mentioned in statics and structural analysis and a number of classes I've had that I've always felt that one of the secret weapons of a structural engineer is your samurai sword or your lightsaber if you're a sci-fi fan, because what I'm talking about is cutting a section, right? You have some load structure, you have some loads, you cut a section, and then you determine, the internal response as a result. Okay. Now, here's the structure. All right. Take the structure, cut a section, and I determine the internal response. Okay. But with that, I'm sort of making an assumption that the only time I'm going to cut a section is like this, perpendicular. No angle cut. But that might not always be the case. See, that makes sense in a lot of civil engineering applications because, for instance, you have a beam. Most of your loads are going to be transverse and whatnot, so that makes sense. But that's not always the case. Sometimes if you're trying to determine what we're going to find here in a second as principal stresses, sometimes you don't want to make a section cut like this. Sometimes you want to make it at an angle. Sometimes you want to, do it that way. And so I think, y'all are smart enough to know that if you cut a section, at like something like an angle, you're going to get different components, right? Sines and cosines are going to be involved in order to determine your components, normal and tangential to the plane and so on and so forth. Now, where does that tie into Mohr Circle? Well, you all should remember from trig that, what are sine and cosine functions? They're really just interpretations of the plot of a circle, right? And so after you do a little bit of derivation, and I'm not going to go through that with you here because we're just doing a review. But after you get through that process of deriving that, you end up arriving at this tool called Mohr Circle. And the idea is that for a given stress state, and we're talking about this in general terms, for a given state of stress, we might have a stress in the x direction, we might have a stress in the y direction, so a sigma x and a sigma y, and we might have a shear stress, a tau xy. For those given quantities, what we can do is we can plot what would the stress state be if you took that section cut and you rotated a bit. Like, what if I cut a section at 5 degrees or 10 degrees or 15 degrees or 20 degrees or 30 degrees? As I rotate the way I look at it, what are my new stresses? And so what does that look like? It's the plot of a circle. The center of that circle is your average axial stress, just sigma x plus sigma y over 2, and your radius is just computed using this formula here. So when you plot it, you end up getting this image that you see on the bottom. This is for a problem that I do and when I teach Engineering 216, but that's kind of what Mohr Circle looks like for this given problem. That's not what it looks like for every problem, but this is generally what it looks like. Your circle is plotted on the x-axis. Your circle's plotted on the x-axis, and it just goes like this. The interesting thing about Mohr Circle is that what it tells you is, it's a very convenient way for you as the engineer to look at what's the worst case scenario. See, when you have a section, it's got all these different stresses. You could cut it at 5 degrees, 10 degrees, 15 degrees. What's the worst way to cut it? What is the direction that's going to give you the biggest stresses? Well, if you look at the plot of the circle, we have really two regions that we're interested in. We're interested in the radius of the circle because if you look at the way the plot is, the highest point on the circle, that's the maximum shear stress, okay? And the maximum shear stress is equal to the radius, okay? So we want to know what's the maximum shear stress. We also want to know what are the principal stresses. The maximum, so you can sort of think of it like this. The radius of the circle is the maximum shear stress. The principal stresses are the maximum normal stresses. And so those are the points on the very, very left of the circle and the very, very right of the circle. And so if you look, actually, I have a typo here because I hear that text box in the bottom says radius of Mohr Circle. That's supposed to say principal stresses. So this right here is supposed to say principal, oh God, like principal stresses. Oh Lord, that is, I apparently really like the letter N because, man, I wrote that big. I'll fix this and update it for you. I hate writing on these slides using the Blackboard interface. But yeah, this part right here is supposed to say principal stresses. So fortunately, you're never really going to have to plot Mohr Circle on the exam. It's going to be very plug and chug. I can almost guarantee you on the exam, you will have a problem that is something like this. You're going to be given a stress state and asked to compute something about it. The maximum shear stress, the principal stresses, and fortunately, it's very plug and chug, okay? So we're going to take this problem and do it together. So given the following, what is most nearly the maximum shear stress? So this is, okay, I've got a structure, I've figured out my axial stress, my bending stress, my shear stress, and so all this stuff, and I'm looking at a particular point, and this is what I got. In the x direction, I have 140 megapascals in compression. In the y direction, I got 205 megapascals in tension, and I've got this shear stress of 100 megapascals. What's the maximum shear stress? Well, from Mohr Circle, I know that the maximum shear stress is equal to the radius of Mohr Circle. So all I got to do is compute the radius, and I'm done. All right. So let's stop this, go to the screen share. Which, by the way, one other thing about Mohr Circle problems is they tend to be very irrespective of unit systems, because all of your problems all of your stresses are given in megapascals and the answers are megapascals. So you can almost kind of, I don't want to say ignore your units, but it ends up not really being that big of a deal. Okay. So all you have to do is compute your radius. And again, what we're doing is, here's your plot. You plot the normal stresses on the x-axis, the shear stresses on the y-axis. And I haven't computed the principal stresses. I don't know what those values are going to be. But let's say it's something, I don't know, like that. This is, you know, one of your principal stresses. This is the other. And this is, you know, that's your maximum shear stress. But that all that's going to be is just, you know, the radius. So if you know the radius, you know your maximum shear stress. And so how do you compute the radius of Mohr Circle? Well, for any given stress state, you take sigma x minus sigma y over 2 and you square it. And you add that to your tau xy. You square that and you take the square root. Kind of like a Pythagorean theorem, huh? Again, not all that complicated. All right, so what do? I start plugging in. I've got minus 140, not 40. 140 minus 205 divided by 2. Take that quantity and square it. Plus, and then 100 squared. And so what does that come out to be? And first off, the units, they're just going to be megapascals. Move that over a bit. Excuse me. $199.4. Do I have a second on that? Good deal. So that's it. What's the closest answer? What is most nearly? C. And I'll show you something real quick. Let me go back to my share. You know, if you look here, you know, what we just determined was the maximum shear stress. If I said, no, I'm not interested in the maximum shear stress. Give me the principal stresses. Again, they're just plug and chug, right? Right here. And this formula looks really, really fancy, but really all it is the average stress plus or minus the radius, right? Because think, there's your average stress there in the middle of the circle, and then you've got your radius. So your average plus your radius gives you one, your average minus your radius gives you another. It's that simple. So even then, the formulas aren't that complicated. So pretty straightforward. Any quick questions? We got a couple minutes. I know we went through this kind of quickly. All right, well, I'll tell you what, this is what we're going to do. I'm going to have a quiz uploaded for you sometime later today. Again, it'll be 5 questions on Mechanics 2, on the stuff we talked about today. What we're going to do on next Wednesday is we're probably going to try and knock out a dynamics review. And then we might want to discuss if we want to keep trucking along with the FE review, or maybe take a break and do something else in the class. Like if we want to keep on trucking with the FE review, we can, but we can also talk about some other topics that we wanted to talk about in the seminar, because there's some other things we can do, but it's sort of up to us if we want to keep on knocking out FE review, or maybe take a little bit of a break for a week. But we'll talk about that next week. We'll go ahead and knock out our dynamics review next week, and then we'll reconvene about that. I might entertain a discussion on Microsoft Teams about that, so make sure you pay attention to the Teams channel. It's 12:50, and I know we're out of time though. But anybody have any quick questions before we sign off? All right. Well, I will fix those. I'll fix these slides, that note here on the slide, and re-upload, and I'll get the quiz uploaded later today. But that's all I have, everybody. I will see you all next week. Y'all stay safe, stay healthy, and we'll see you next week.